Hello and welcome back to Calculus 2, section 7.3 on hyperbolic functions. Now, these are new functions you guys didn't study before. You know polynomial functions, exponential functions, trigonometric functions, logarithmic functions, rational functions, radical functions, right? Whole bunch of these functions you learned before, starting in algebra, going through pre-calc 1 and 2. These are new now. And, sorry to say, confusing because they're going to be similar to trig, but not going to have anything to do with trig. So, let's see what these guys are. Hundreds of years ago, one of the gods of mathematics, Leonhard Euler, said, here is a formula that works. And people were amazed. He wrote, when I have to, sine x is equal to e to the x, e to the ix, complex ix minus e to the minus ix divided by 2I. So on one side you have a trig function, on the other side you have exponential functions, and also the complex I. That I was, if you remember, square root of -1. He also said that the cosine of x is equal to e to the ix plus e to the negative ix divided by 2, no I. And if you run trigonometric identities using sines and cosines, and you run trigonometric identities using these e's, observing the complex I rules and all of that kind of stuff, most of which you don't know right now, it all works out. Because these are, these formulas work, right? Now, he was one of the most productive mathematicians. No, he was the most productive mathematician of all time. If you want to buy the collective works of Euler, it's about 72 books of papers on mathematics, and it's about $11,000. It's called Opera Omnia, so you can start saving. He used to produce papers every week. And for most of his life, he was blind. So he was dictating these things to scribes around the desk. He was working out all of these things, developing this mathematics in his head. So the square root of -1 with I, including the entire complex mathematics. When he made those definitions, he doubled mathematics of his time. Newton didn't know about trig. There was no trig for Newton to take derivatives. And Newton worked on polynomials because this is what Newton needed. It's a parabola, -x squared, right? Let's do the derivative, figure out the gravity, do some physics. Boom, immortal forever, right? Now, what Euler did is define what, you know the number E stands for Euler. That's the constant he came up with, right? And in the honor of the mathematician, you have now E. So what do we have? We have all of the exponential stuff. You have the logarithmic function, ln, and everything there, plus all of these combinations like this. Then you have the whole complex numbers deal and all of that kind of stuff. A whole bunch of geometry and so on. But you have to have a lot of things to fit in 72 books, right? It's not, it's not one calculus textbook of stuff. It's a lot of things, right? So, this was known, and then he said, and then, all the trig identities and everything else, right? And then he said, what happens if I remove i's? what happens if I write the same formulas on the right and just delete i's? And then obviously he worked out the mathematics of all of that in his head, and then came up with a whole branch of hyperbolic functions, and then he called the scribes over so that can all be written down, so today we can learn about it. And one of the applications that is used today, which is when you hang a cord, right, between its cord that sags, right, due to gravity. If you hang a cord between 2 points, like your telephone lines and the power lines and so on, right, it will sag according to the function that we are going to learn tonight. So there are a lot of other applications, obviously, but this one is extremely important because we want electricity, right? And if you want the electricity, you have to stretch power lines. Now, to stretch power lines, you have to introduce the sag, because what happens when it's extremely cold outside? What happens to objects when it's extremely cold? They shrink. So if the power line between two towers is stretched at tension, and then it's cold, when it shrinks, what happens? It's either going to snap or it's going to rip the tower right out. And each one of those towers with a set of wires attached to it is 100K. So you kind of don't want to have that. Now, can you have it just sag on any arbitrary length? What happens when it's too hot? It's going to expand, so it's going to sag even more. And then the truck is going to, hit it. So as engineer working, let's say, electrical engineering power lines, right? You're designing these things, and you will be using one of the functions to compute the sag, all right? So these are the things that we are going to use. So Euler said, yeah, this is all cool, right? Let's see, what can we get if I say just e to the x minus e to the minus x over 2 without any i's? Worked out properties of that, and then he said, what happens if I have e to the x plus e to the negative x over 2? Worked out properties of that, and found out that the properties of these functions, the identities and whole bunch of stuff that arises, reminds of trig so much without being anything like trig. Holy nightmare, right? So he named them hyperbolic functions, and the one on the left is going to be called sine hyperbolic x. One on the right is going to be cosine hyperbolic x. And these two have nothing to do with sine and cosine. So, this is your life for this lecture. We're going to do more. So I'm just going to put also the box and the cloud. So you get the box and the cloud on this one. These two, if someone shakes you out of bed at 4:30 and asks you, you need to know them, right?
So this is the first exam?
This is the first exam, exactly. You are going to have these problems on the first exam. You will have to use these thru formulas 100% in a problem. Okay, so now, the most important thing now is to write the sentence that these are not trig functions. Write it in blood. If you don't have red, just, these are not trig functions. Because everything, here, scream it, everything about this will remind you of trig functions. Now, why is this so important? Guys, trigonometric functions are periodic functions. You go a little bit, and the trig function repeats itself. Sine is the infinite wave. Cosine is the infinite wave. Tangent keeps repeating itself after every asymptote the same way. All 6 trigonometric functions are periodic. Sure, we draw only one period, and mainly we work with one period, but they are all periodic from negative infinity to positive infinity. Trig function repeats its period infinitely many times. Hyperbolic functions are not periodic. What is a non-periodic? X squared is not periodic, right? It's just a function. E to the x is not periodic, right? So these functions are not periodic functions, and therefore they have nothing to do with trig functions. However, being that their definitions are so close to trig functions, they exhibit properties like trig functions. So you are going to have identities to work out the same way you worked out identities for trig, except they are going to be different slightly, just to be confusing as hell. So you learned that sine squared x plus cosine squared x is equal to 1.
Sorry.
Now you are going to have cosine hyperbolic squared x minus sine hyperbolic squared x is equal to 1. Now you know what sine squared minus what cosine squared minus sine squared was? It was cosine 2x. So the formulas actually switch. Oh, it's gonna be a trip. But the idea is to understand that these functions are not periodic functions, and they will have their use in the universe. Now, when you add
Did you say cosine squared hyperbolic x, or
no, cosine squared x minus sine squared x is going to be cosine 2x, cosine squared hyperbolic, cosine hyperbolic squared minus sine hyperbolic squared is equal to 1.
Okay.
So you see that they both have the form and then have different answers. So, bah. And then some will be the same. Anyway. What was I talking about? Yes. So when you are looking at these functions, you obviously have to shovel these e's around. And the first half of the lecture is technically talking about the function and talking about identities, which is like a pre-calculus part of it. And then the second half is derivative and integral of all of these. So we are going to introduce like 50 formulas here, 50 in this one lecture, right? But you have seen these formulas in trig, and they are just slightly different. And I know, it gets annoying, but such is life. So the first thing we want to define is now tangent hyperbolic x. Oh, by the way, you need to star this section if you are taking differential equations. Your second order differential equations, half of them will have solutions with trig, and the other half will have solutions with these guys. So if you're taking difficu, right, you won't be able to do half of your exam too if you don't know this. So get on board. Let's go. Tangent hyperbolic x is naturally sine hyperbolic x divided by cosine hyperbolic x, which in the e form would be e to the x minus e to the minus x over e to the x plus e to the minus x. Those 2's cancel. That's your tangent. Your cotangent hyperbolic x is obviously upside down. So plus on top, minus on the bottom for ease. Your secant hyperbolic x is going to be 1 over cosine hyperbolic x, which is 2 on top, and then e to the x plus e to the minus x. And cosecant hyperbolic x is 1 over sine hyperbolic x, which is 2 over e to the x minus e to the minus x. And you got your other 4 hyperbolic functions. Do we have inverse hyperbolic functions? Yes, of course we do. Stay tuned, right? Those will all have ln's instead of e's because, right, e's are e's and ln's are inverses of those. If you want inverse hyperbolic functions, well, they better be working with ln's. But we need to get there. So now I'm going to show you all of the graphs on the screen so you can see it. I'm just going to Google the sheet that has all 6 of them in one spot. Yes?
So on the test, will you be using this sine?
Yes.
Just those 2?
Yeah, I'm sorry you're disappointed.
Okay. No.
I am searching hyperbolic functions graphs. I'm going to click on the first image that pops up on Google and do the image in a new tab and make it as large as possible so we can see them all. Oops, and then switch. So this is literally the first image that popped out. You can do the same thing and print it if you want to. So which one of these is a sagging chord for electrical engineering? Cosine hyperbolic x, yes. Top row, middle. That's your sagging chord. Anything you hang as a rope or a chain or a cable, it's going to be modeled using cosine hyperbolic x. Right underneath that one is one that you can use for normal distribution in probability. You remember the bell-shaped curve? There's the bell-shaped curve right there. You can use this one to model as well. So you don't have to use the integral of e to the negative x squared. That one is tough to compute. Yes?
What's the difference between cosine hyperbolic and like a regular parabola?
Oh, there is an excellent question. You know what you're going to do? You're going to graph them both on the same graph paper, and you're going to see what the difference is, right? Now, the obvious difference here, right, for cosine hyperbolic is that your x squared is going to go through 0. Your cosine goes through 1. Now, this is not cosine hyperbolic shifted up 1. So your x squared will be x squared plus 1 to match this. And they're still, now, they are not going to rise in a curve at the same rate. So when you throw, what happened to the, well, it's somewhere over there. Oh, there it is. The experiment I did when I said Newton worried about this, that was negative 1/2 gt squared on the equation for physics. And that was negative t squared, parabola open down. So when we throw things, they're going to fall with a parabolic shape. If you hang something, it's not going to be x squared, it's going to be this function. So that's the world works, right? That's the nature, and we have the function in mathematics that helps you as an engineer, right, do the proper modeling so you can calculate exactly what it means. So we kind of see that the cotangent hyperbolic almost looks like 1 over x. No, it's not, right? Because it has horizontal asymptotes at -1 and 1, right? So it's not 1 over x, but it kind of resembles it, right? Also going for the cosecant hyperbolic over there, and so on. This one looks like x cubed or a tangent, and that's our sine hyperbolic, right? So the shapes are very familiar without being what you actually see. And then the names are all going with trig functions, and they have nothing to do. None of these functions repeat after a period, because there's no period. These are not periodic functions, and they do not repeat. So you're not going to find another cup like this again, like you are going to find for secant and cosecant hyperbolic. Your secant hyperbolic has a whole bunch of these, infinitely many cups open up and infinitely many cups going down, right? For both secant hyperbolic and, secant and cosecant trig functions. Over here, no periodic behavior. This is like, one shot, a graph, and that's it. It ends. I mean, it doesn't end, it goes to infinity, but it doesn't repeat again. Yes?
It looks like cosecant hyperbolic
Cosecant hyperbolic right here.
ends at 4.
No, they go to infinity. It's just,
Okay, got it. That's just how it's written.
yeah. I mean, all of them, the way they graph, right? They all end at 4, but no, they don't.
Okay, got it.
They shoot forever. So these are completely new functions, guys, that are introduced to you today. It's highly recommended you Google this image. When I typed in hyperbolic function graphs, this is the first picture that came up in Google. I opened that one. If you print that and glue that on your back, why is that important? Domain and range, right? All real numbers, domain and range, both over here. All real numbers on domain, range 1 and above. Over here, 2 asymptotes stuck between 2 values. Over here, what is the range for this one? Domain is all real numbers. I asked about range. 0 to 1. Excluding 0, including 1. So parenthesis, 0, 1, bracket, right? So domain and range for all of these. X-intercepts, Y-intercepts, symmetry lines, all of those things you learned in Trig calculus that you apply to polynomials and all other functions you learned, you get to do this here as well. What is the cosecant x-intercept? Cosecant hyperbolic. What's the x-intercept for cosecant hyperbolic?
You said the x.
Yeah.
There is none.
There is none. How about the y-intercept for cosecant hyperbolic? No. How about cotangent hyperbolic? Y-intercept? None. How about secant hyperbolic? Y-intercept? 1. X and y intercepts for tangent hyperbolic at 0, both of them, right? You see these things because you know that the x-intercept means cuts through x-axis, y-intercept means cuts through y-axis, and if you have the graph, you just look at the graph. So x-intercept 0, no x-intercept, x-intercept 0, no x-intercept. Y-intercepts 0, 1, 0, no, 1, and no. So domain, range, x-intercept, y-intercept, and asymptotes, all of those are your pre-calculus concepts that are considered for every function. And by looking at the graph, you can decide it. So guys, you are learning 6 new functions. These are completely new functions you have never dealt before. So you are treating this class today like learning x squared function for the first time, right? That's what you're doing, or learning ln x for the first time. So that's what you're doing now, 6 functions in one shot. All of them have domain, all of them have range, all of them have x and y intercepts, All of them have asymptotes or not, but all of those features are there on a pile. The two functions that you need to know everything about, obviously, will be sine and cosine hyperbolic, because those two, as you can see in our box over here, those two give rise and birth to all other four. So you should be able to take care of about 90% of the stuff in calculus just using sine hyperbolic and cosine hyperbolic. The other 10% you will take care with a secant and tangent hyperbolic, because there will be eventually derivatives and integrals. So, they pop up as well. So now, being that so far they behave like trig functions, we would like to know if there are certain trig identities that, trig-like, if there are some hyperbolic function identities that we can work out and then use our definition with ease to prove them. And that's a lot of fun because it's just a whole bunch of algebra, no calculus, right? Whole bunch of algebra, and you just, plow through those calculations. So let's take a look at identities. Now, those identities are listed in your book, and if I ask you to prove any of these identities, obviously I will write down the identity. Since not everyone is going to differential equations, not all of you need stuff. Now, even if you're going to differential equations, you're not going to need all of these identities, just basic few. I'm going to list 10 identities that are given in the book, and probably work out 2 out of 10, leaving you to practice the other 8. And then for the exam, we're going to have one of those 10 for you to, show off your math skills in algebra, right? So let's list them all. The first one is the cosine hyperbolic squared minus of x minus sine hyperbolic squared of x is equal to 1. One minus tangent hyperbolic squared x is equal to secant hyperbolic squared x. Cotangent hyperbolic squared x minus 1 is equal to cosecant hyperbolic squared x. Then we have cosine hyperbolic of x plus y, sum of two values, is going to be cosine hyperbolic x cosine hyperbolic y plus sine hyperbolic x sine hyperbolic y. This is one of the very dangerous formulas, because for trig, you have the same setup. This is a minus. Hi. Yes, but let's do let's write them out first. Sine hyperbolic x plus y is going to be sine hyperbolic x cosine hyperbolic y plus cosine hyperbolic x sine hyperbolic y. You're going to love the next one. Sine hyperbolic squared x plus cosine hyperbolic squared x is equal to cosine hyperbolic 2x. For trig, that's equal to 1. And this one is equal to 2x, cosine 2x, right? They're completely swapped. This one is no-brainer. Sine hyperbolic 2x is 2 sine hyperbolic x cosine hyperbolic x. That one is the same as the trig one.
Yeah.
You delete ages on this one, you get the same as trig identity. So that one is the same. So far we have two that are the same as trig. This one is the same and this one is the same. Everything else is different in some way. Yes?
The one before the last one, is it equals cosine h2x or squared x?
2x. 2x as a double angle. Double angle. And remember how much I talked about the power reducing? That you have to learn the cosine squared and the sine squared, otherwise you can't integrate in this class? Well, here we go. Cosine hyperbolic squared x is equal to cosine hyperbolic 2x plus 1 over 2. That's the same formula you had for trig. And then here's your sine hyperbolic squared x is cosine hyperbolic 2x minus 1 over 2. Those are swapped for trig. And then there they are.
Is that 2x or x? Or h squared?
That's a square, that's a 2. 2, 4, 6, 8, 10. Good. There are also formulas that give you the odd property, odd and even property. So cosine hyperbolic of negative x is the same as the cosine hyperbolic of x. It's an even function. You saw that on a graph because it looked like x squared shifted up. Sine hyperbolic negative x is odd function, so minus sine hyperbolic of x, and tangent as well is also odd function. So that's 12 formulas right there, and the 6 before we're already at 18, and we haven't scratched the surface yet.
This is all 7.3.
Yes, the first 25% of it. It took you a month to study. It took you a month to study polynomials, right? In pre-calc 1. Then you took 3 months to study trig in pre-calc 2. It's a lot of stuff, right? And now we're doing the equivalent amount of work in one lesson. So think of all your pre-calc 2 3 months of trig mushed in one lesson now, adding the calculus, right? Because you didn't do derivatives and integrals of trig in your pre-calc 2 course, right? You did a unit circle for like a month, right? All right, let's prove any of these. Prove number what?
Which one's your favorite one that you might put on the test?
Well, I'll just pick something else.
Number 7.
Number 7, you said. Okay. 1, 2, 3, 4, 5, 6, 7. Sine 2x. Okay. So prove number 7. That's 8. That's 9. 10 and 11 and 12. So prove number 7. Sine hyperbolic 2x is equal to 2 sine hyperbolic x cosine hyperbolic x. Guys, the way I do this problem is the way you do all 12 of these. All 12 work out the same way. So I'm going to write out the sine. So let me just write here, orange. Use sine hyperbolic of a flower is equal to e to the flower minus e to the negative flower divided by 2. Why am I using a flower?
Because you want to.
Why am I using a flower? Why am I not using x? Because I have 2x on one side. So for one side of this equation, my flower is 2x. On the other side of the equation, my flower is single x.
So it's just whatever's inside.
Thank you. Whatever the argument of the hyperbolic function is going to be the exponent of e. If I have 2x, it's 2x. If I have 5x, it's 5x. And then we'll have to work out our exponents from, right? Also use the cosine hyperbolic of a heart is going to be e to the heart minus e to the negative, no, plus e to the negative heart divided by 2. All right, now that we coded that, we have e to the 2x minus e to the minus 2x over 2 equals to 2 times e to the x minus e to the 2x, oh sorry, minus e to the minus x divided by 2 times e to the x plus e to the minus x over 2. All right, so now I replaced the sign over here with what that sign is as the formula with ease.